The next setting to talk about is gain and the exponents. Think of gain like this. As we add in these additional layers of noise for the detail, it's essentially adding to the value that was there before. And so with the gain, if you turn this to a lower value, say like 0.1, what's going to happen is that it's going to allow the subsequent layers to add more to the original value. In practice, what that means is that the layers become more noticeable. It adds a little bit more of a contrasted look as compared to, let's say, turning the gain up like that. So if you want the detail to feel a little bit more rough, and sometimes you'll see this as roughness too, I believe, then go ahead and turn that gain down, and that will essentially do it. A lot of times too with these parameters, you just want to play with the settings to see what they do. And I think gain is definitely one of those things. Now this exponent here refers to something called the Minkowski distance function. And what that basically is trying to describe is how far away these cells are allowed to be from each other. So as we turn this up, the cells try to get further and further away from each other. As we go down, the cells are cool with being closer to one another. That, in general, is what this exponent is trying to do. And perhaps a better illustration of this is in this website right here, this scicomp something. This is probably a good example right here. So the higher the exponent of, or the more the square the cells become, an exponent less than 1 produces star shapes, while values of 1 are the same as using a Manhattan distance metric. So, visually speaking, if we go down here, you can really see what some of these things are doing. By the way, if you want to get more technical with these noises, I will include some resources towards the end of this video, just in case you want to dive in and kind of figure out more the technical mathematics behind these things. But anyway, that's what this exponent is talking about. It's controlling the shape of these cells. And another thing to keep in mind here is that if you use a different type of noise that's not cellular, you won't have this exponent available to you. So if we said hamma, look at that, we don't have any other options. It all gets grayed out. And it just depends on the algorithm and how it works. That's why these things get grayed out, or that's why sometimes you have an exponent. In this case, the hamma is not taking advantage of the Minkowski formula, so that's why it's grayed out. Anyway, that's what that's all talking about. Like I said before, a lot of this stuff is just playing with the parameters and seeing what they do visually. The next section right here is the animation section. And I think that animated textures are something that's very, very underrated by a lot of people when it comes to how cool they are and what they can do. So as an example, let's take our speed to 1, and the time source is global, so that means it'll just use our timeline down here. If I press play, we have animation, which, you know, it's not that surprising, but if you take a step back and think about this for a second, that means if we, let's say, plug this into displacements or something like that, we can create some really intricate, trippy-looking effects without having to make everything from scratch, without having to make all of these algorithms from scratch like you might typically do in a VOP context. So again, that's kind of a pretty big deal if you're, let's say, a motion graphics artist who wants to have your stuff look different than everyone else's stuff. If you rely on some of these noises that animate, it gives you a fully procedural system that allows you to change movements. You can also animate this manually by going to the time source and saying custom, and with this custom time, now we can do something custom. So say 0, 1, and then let's have it speed up towards the end. We'll go a keyframe of 5. Now if I press play, it's going to start really slow and get faster and faster. And now it's going to really kick up until we get all the way to a speed of 5. So that gives you an idea of what this custom time will do. Something else that's cool is that this custom time will enable you to have repeatable effects. So let's say the custom time is 0, and we say we go up to 5, and then let's go back down to 0 again. Check this out. We can have a seamless loop. So it's going, it's kind of doing its thing, and then it can go back down and not skip a beat. So a really cool way of creating repeatable animations. This animation section right here is very, very powerful, and you can do a lot of great stuff with it. So it's worth experimenting in the future for sure. Next up, we have the inputs, which is essentially the manifold or the texture space that I was telling you about in the very first video. In Redshift, it's called the source. If you were to use, let's say, Karma or Mantra, you would use a point VOP. And just to show you the correlation, let's say you go to make a noise. It's the same thing as what you plug in right here to this position. It's determining how the noise will stick to the object. In VOPs, by the way, if you want to use object space, you would go to the position like that. If you were to use world, you would use a constant and just set that to the origin. So you would use a vector 0, 0, 0, and you would do something like that. And if you wanted to use UV or rest coordinates, you might try to use a bind and say either rest or UV. And that would eventually become a vector and plug into your position. So this is how it works in VOPs. In Redshift, it's the same dang thing, except now we have the source, UV vertex attribute, object, or world. Keep in mind that if you use the rest position, so let's say that this is a character, the skin's deforming, in other words, the points on the surface are deforming, that's separate from the object overall, right? So if that's happening, then you need to use this UV vertex attribute, specify, let's say, rest, and within Houdini, you would then specify rest, a rest attribute, a rest coordinates, by saying rest position, like that. If you middle mouse, it's going to say rest as a point position, but we can use an attribute promotes to make that a vertex attributes. So now we'll say rest, vertex, rest right there. And now that would be picked up by Redshift right here as a vertex attribute. So again, I just want to reiterate what the whole rest thing is for. If you have points moving on the surface, if they move along the object, then in order to get your noise to stick to that object, you need to tell it to use the rest coordinates. The rest is basically the coordinates of whatever the object is before it gets deformed. And so that's how that works. It's like the rest is no deformation. If you're, let's say you have skin stretching or something like that, you don't want any swimming with the noise, so you tell it to look at the undeformed mesh positions by saying rest. And that's how that generally works. We're almost done with these parameters. We also have this overall scale and the scale. This in Redshift is the same thing as frequency. So if we go like that, I think pretty self-explanatory, really. Do keep in mind, though, that you can get some very interesting effects by scaling up in the Y direction. So we can change these noises and make them look really interesting by warping them in this sense. This might be really cool for, let's say, some caustics on an ocean floor. So with this, you can do some really cool things. And we'll also talk about this coordinate scale right here, because this becomes very important when we're trying to really change our noises. But anyway, this is essentially the same thing as frequency. We also have an offset. And think of this as offsetting the position of the locator when this goes to attach itself to the object. So remember how I said in the water bottle example, a locator attaches itself to the water bottle and the noise attaches itself to the locator? Well, think of this offset as offsetting the locator. You can cause things to swim just by changing the locator. And the nice thing about this is that if you use, let's say, this offset in conjunction with a repeating animation, it could allow you to create a repeatable animation that doesn't stop in the middle so that it's repeating infinitely and it doesn't have that weird spot where it tries to rewind itself. So by animating this in a clever way, you can achieve between the offset and the animation an infinite loop without it stopping in the middle and going backwards. Kind of cool. Anyway, we'll talk about that here later on, but I just want to give you a preview of what that could be used for. On the output here, we have the cycles. To be honest with you, I've tried finding a more technical definition for this thing. I really can't find it. It's not in the Redshift documentation, but it's really cool. It just adds some repeating patterns, I suppose, to whatever the thing is. So play with that. It could get you something really neat. We have the low clip. This clips out your blacks like that. High clip clips out your whites, meaning that if we're at, let's say, 50% here, anything that's 50% or above is now 1. Likewise with the low clip, if we go 50%, if anything's 50% gray or below, it rounds to 0 now. So that's the clipping. Brightness, like that. And then, last but not least, the contrast. Okay, so there you go. That is all the main noise settings here for Redshift. Now that you know this, we have a lot of options now to really have fun with this. In the next video, we're going to now dive into the tower scene. I'll show you a very simple workflow, a more intermediate, and then a complicated, complex workflow involving these noises and the different ways you can go about using these sort of things.